In this lesson, we're going to look at solving counting problems. And all that means is that we're taking everything that we learned in this unit and putting it together. So your responsibility now is to look at each question that you are faced with, like on a test, on an exam, on an assignment, and decide, is this fundamental counting principle? Is this a permutation? Is it a combination? Do I do an exponent here? Right? Is this a factorial type problem? What is it that I'm doing? So always identify what is it that you're given, right? What is known, what is unknown, what are you trying to solve for, and does order matter, does order not matter, right? Those are all the questions you're going to ask yourself as you're going to go through these types of questions. So we're going to do a couple together, and then we'll do more in class. So it says a piano teacher and her students are having a group photograph taken. There are 3 boys and 5 girls. The photographer wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the students and teacher sit in a row of 9 chairs for this pose? So I always like whenever we get these types of questions, like the red car question, draw out the dashes, right? Let's draw that out. So we've got, how many people here total? It says there are 3 boys and 5 girls. And then you've also got the teacher. So alright, so there we go. That will accommodate the row of 9 chairs for this pose. Now, the boys are sitting together, right? So let's do the 3 boys here. And then we've got the 5 girls. And then finally we've got the 1 teacher. Now, the 3 boys themselves can sit in the first, second, or third position, and then they can have all the different arrangements in those 3 positions. So that would give me 3 times 2 times 1, or 3 factorial, right? So if we just use the boys here in those 3 positions, any of the 3 could sit here. Once the 1 kid sits down, then any 2, and once that person sits down, then that's the last one, right? And that would give us 3 factorial. Now, if you look at the girls, same idea. Within those 5 spots, any of the 5 could sit here. Once that person sits down, 4, then 3, then 2, then 1, right? And that would be the same as 5 factorial. And then the teacher, well, there's only 1 teacher, so there's only 1 way for the teacher to sit there. So this would be 5 factorial, and this would be 1. And at that point, you kind of feel like you're done, right? I've done all the math, I've done all the work, and that's fine. However, these 3 students that are sitting here can be moved to this position or can be moved to that position, right? So there's more than just that position for 3 factorial. The 3 factorial can sit where it is, or it can move in the middle position or at the end. And then if you look at the 5 girls, they can stay where they are, or they can go here, or they can go here. Right? And then the teacher could sit in the middle between the boys and girls, can sit at this end, or the teacher could sit at the end that they already are sitting. So how do we accommodate that? Okay. So because we're treating this kind of like 3 different objects, right? If I scroll this down, we've got the boys in one position, the girls in another position, and the teacher in another position, but they can all move between their positions. So if I have those 3 objects to choose from, I would have either the boys or the girls or the teacher there. Once one of those groups are placed, then I have the other 2 groups that can be placed there and the last group to be placed there. So this is accommodating the various groups that could sit in those positions. which would be 3 factorial. But it's not just the groups, it's also within the groups. The 3 boys are 3 factorial, the 5 girls are 5 factorial, and the teacher's 1. So the answer here for the number of arrangements would be exactly what I was just saying, 3 factorial times 5 factorial times 1, which is what we're seeing up top, but then all of that is going to be multiplied by the 3 factorial. So, and we can move those groups around to give us 4,320 ways to arrange that group. Okay, so you might want to go back and look that over again, but we get those types of questions often. We'll do some more practice in class. Okay, let's take a look at the next one. Okay, so these types of questions come up, and I'm going to explain how to recognize that it's this type of question. There's always going to be variations, but I'll explain how we can see that. It says combination problems are common in computer science. Suppose there's a set of 10 different data items represented by the letters A through J. Now those items are to be placed in 4 different memory cells on a computer. Only 3 data items are to be placed in the first cell, 4 in the second, 2 in the third, and 1 data item in the last cell. How many different ways can 10 data items be placed in the 4 memory cells? Now, if the fact that we're dealing with computer stuff is completely throwing you, like, I don't understand what they're talking about, you can think of this as in people being placed in cars. You can think about, like, to get a ride. You can think about this in terms of students being placed in classrooms to work on things. You can think about this as maybe filling boxes with donuts, like whatever you want to do. You have so much stuff, right? 10 different items of stuff. In this case, it's data items, and it's to be placed in different spots. Now you got to think, once you've placed something in a spot, you're not taking it out of its spot anymore. It's already there. Okay? So thinking about this, we've got A through J, right? All those different items. And we want to know how many ways can the 10 data items be placed in 4 memory cells. So we're going to look at the number of ways that we can put them into cell 1, the number of ways in cell 2, the number of ways in cell 3, the number of ways in cell 4. Now you can see I wrote and in between all of them, and remember and means multiply because all of that has to hold true. Okay? Not or, but and. It's not different cases. All of these things are happening for that problem to be solved. Now, order doesn't matter. It doesn't matter what data item gets played in cell 1 in what order. It just matters that all of the items are in that cell. So this is not going to be a permutation type question, but rather a combination type question. Okay, as long as everybody is in that place. So if I look at the first cell, okay, we have 10 different data items to choose from. But if we go back here, it says only 3 data items are to be placed in the first cell. So I can only put 3 in here. Okay, so those 3, assume that those 3 are there. Well, that means I only have 7 left to place, right? I'm not going to take them back out. Think about donuts in a donut box. You have 10 donuts to distribute, right? You've taken 3 of the donuts, put them in that box. You only have 7 left to put into box 2, box 3, and box 4. Although I wrote cell 3 again. 4. Okay, so in cell 2, I only have 7 left to choose from, but in the second cell, it says we've got 4 items can be placed there. Well, those are taken care of now. I only have 3 left. 3 left to place in data cell 3, and that would be 2 items that can be placed in there. So it's 3C2. Well, 3 minus 2, I'm only left with 1. So finally in cell 4, it says there's only 1 data item that can be placed there. and that would be 1C1. Okay, so we've placed everything, 3 in cell 1, 4 in cell 2, 2 in cell 3, and 1 in cell 1. The only thing that's different here between this and the other cases that we've been looking at, or the other examples, is that now how many you have to choose from is decreasing after you've placed them. Multiplying those together, okay, multiplying all that math together after you figured those all out, you end up with, now you can put it all in your calculator in one shot, or you can do them individually. Double check when you punch that in that you get the same answer with me as 12,600 ways. Okay. The last example we're going to look at is example 3, and this has to do with a deck of cards. So it says, how many different 5-card hands that contain at most one black card can be dealt to one person from the standard deck of playing cards? So again, you need to be familiar with a standard deck of playing cards. Key information here, at most. And when I see at most, that means I have to deal with cases. So at most, one black card means that we can either have one black card or no black cards. Okay? And we're going to have to deal with both of those cases. So let's take a look at case 1. So if we have one black card and 4 red cards, right? How many black cards are there in a deck of cards? 26. But we only want 1. And then how many red cards do we have in a deck of cards? 26. And we want 4 of those. Because it's one black card and 4 red cards, we're going to multiply that together. Case 2. What if there are no black cards and 5 red cards? Well, that would look the same, but it would be 26C0 times 26C5. Get those two answers, add them together, right? And you'll get, well, I'm going to rewrite this. 26 C1 times 26C4. Do all of that stuff first because order of operations matters here. 26C0 times 26C5. And then do all that stuff next. Once you get those two answers, add them together. And you get a total of 454,480 ways. Okay? So again, at least, at most tells you we're dealing with cases. Okay? In each case, one black card and 4 red cards, we're multiplying those two combinations together because both have to hold true. And then looking at each individual case, we're adding them together because it could be case 1 or case 2 to get the sum. Thanks for joining me today.